Okay, hello, welcome to the Navigating Now podcast. My name is Joe Bodu. I'm a second year PhD student here at a joint school of nano engineering and nanoscience. Today, we have our seminar series guest speaker for today, Jie Liu?
Yeah.
Jie Liu of Duke University. He did his Bachelor of Science and Master's of Science in China, and then
Shandong University.
Shandong University in China before doing his PhD at Harvard University before becoming a professor at Duke.
Thank you.
So very interesting presentation today.
Thank you.
Mostly about photocatalysis.
Yes.
I just got introduced to photocatalysis today.
Okay.
Or kind of actually had a name to it. And I think it's really interesting how here's this concept that everybody pays attention to, right? But no one pays attention to this other thing that's also a part of the process, the non-thermal effect.
Yes.
Right? People don't pay attention to the process. Maybe we could get some sort of benefit into it. And I understand one of your grad students actually was kind of like the catalyst, no pun intended, of kind of this process. I feel like a lot of things, kind of like a lot of research directions, usually come not unintentionally. So was it kind of one of those things, or was it kind of like a meditated?
That's a very interesting question. Actually, I have a very interesting story to tell. When we first work on plasmonic material, especially rhodium, which is a very good UV plasmonic material. So at the beginning, we didn't start working on catalysis. So like everybody else who work on plasmonic materials, we first thought of surface enhanced Raman spectroscopy, which is another application for plasmonic materials. So we made these nanotubes of rhodium, and we use it as a substrate for surface enhanced Raman spectroscopy. We did see enhancement, very good enhancement of the signal in the Raman spectroscopy, but my student tell me, okay, the signal only lasts for 10 seconds. 10 seconds later, signal disappear. So we were quite disappointed about it, and because you don't want to only look at your, your target material for like 10 seconds, then they disappear. We did publish a paper and show that this is a good plasmonic enhancement, that there are good enhancement from this material, but lifetime is short. We had a long discussion with the graduate student, the first student working on this, Xiao Zhang. We say, why it disappear? No, the simple reason is that they disappear because they were decomposed. The high energy electron generated by the plasmonic nanoparticles did something to decompose the molecule on the surface. Then we turn around and say, oh, if that's the case, why we don't do chemistry with it? Why don't we use these high energy electrons to do chemistry and do catalysis? That's when we started looking for papers that people did in plasmonic assisted photocatalysis and also plasmonic catalysis. That's how we got into the whole field of plasmonic catalysis. I wouldn't call it a field experiment. It's an unexpected experimental result that led us to this exciting research field.
So that's interesting. So there was a hypothesis that the electrons had decomposed, right?
Yes.
And in order to prove that hypothesis, if you had done chemistry with it and there was a reaction that proved your point, or did you actually understand the electrons decompose?
I thought we understand at the beginning. I thought it was an easy process. Reading papers, people publishing in plasmonic catalysis, it is a high energy electron that affect the stability of the molecule on the surface of metal nanoparticles.
Right.
I thought it was simply just electron transfer from the metal nanoparticle to the absorbed chemical that, like photocatalysis, cause chemical reaction that change that into something else. Right. It's surprisingly more complicated than I originally thought. The rest I talked about at the seminar. So we first discovered that light shining on plasmonic nanostructure can affect a chemical selectivity of a chemical reaction. That's our first paper. Then we got another unexpected result. It's like the kind of efficiency of light is too high to be anything reasonable. Then that led us to start looking at the thermal effect. So after we discovered there are significant thermal effects, we developed experimental method to separate the very complicated tangled thermal and non-thermal effect experimentally. We now have 3 ways to do that to kind of separate the thermal and non-thermal effect in our experiment. So once we separate that, we can study what part is due to thermal, what part is due to, I'll call it non-thermal, and how can we enhance each of them separately and more recently enhance them as an overall effect from light. So because plasmonic catalysis has a thermal part and non-thermal part, it opens a lot of new possibilities that we cannot do in the traditional photocatalysis. Traditional photocatalysis, only the amount of light with energy higher than the band gap of a semiconductor can be used. The rest is wasted. Plasmonic catalysis, there's a possibility that we can use the full spectrum of sunlight by tuning our catalyst composition, by tuning the relative contribution from thermal and non-thermal effects in plasmonic catalysis. We can design a catalyst that would respond to solar light most effectively. That's something that I'm really excited about, and that's a real possibility that we can do it.
Okay. So, because sometimes we have viewers who've not been in research or kind of near academia. Mm-hmm. All right. So, can you explain to me plasmonic photocatalysis like I am a 5-year-old?
Okay, plasmonic photocatalysis is like we have a tiny metal nanoparticle that is antenna for light.
What's a nanoparticle? I'm just kidding.
Nanoparticle is a tiny metal particle.
Okay.
That behave like antenna for light, that can absorb light effectively, and somehow affect the chemical reaction happen on this metal surface. Okay. There are different mechanisms. I call it thermal and non-thermal. Thermal is a traditional, very old catalysis field. Non-thermal is totally new for plasmonic nanoparticles. It's mediated by something called hot electron, which is the high energy electron that is generated by absorbing light from the metal nanoparticle. Yeah. So 5-year-old, probably still too hard.
I think 5-year-olds know what effective means. So
they know antenna.
Yeah. I think that's a pretty good explanation. I think science is going. I feel like I've noticed a trend in science where they're more exploring those areas where I guess, how do I say this? Not irony, but those traditionally counterintuitive areas within different fields. For instance, there's like non-woven materials now, but people have been studying woven materials forever, right?
Yeah.
And then now you're studying non-thermal effects of photocatalysis, and in addition to a different version of photocatalysis, because now you're getting to plasmonic photocatalysis, which is just a whole different ballgame in itself. And I did have a question. So your student, Lucy, right, who graduated, did a postdoc, and is not working. You wanted her to go into academia. Right. And she voted against that. I'm pretty sure her time with you was splendid, but what's that version towards academia versus...
Okay, Lucy, listen to this, okay? Lucy has all the character and the capability that a successful academic researcher would have. She is very careful doing experiments, observative, and pay attention to details, and able to solve problems experimentally. Not only that, she writes really well. She can produce a manuscript to me. I can only go there, change a few sentences before I submit for publication. She has all the capability to be very, very successful in an academic environment. Why she choose not to do that? You have to ask her yourself. But my understanding, Lucy, correct me if I'm wrong, is that she always tells me that her father has a really, really good life as an industry researcher in a big company. She wants to do that since she was very, very young. I was not able to change her mind, change her feeling about being a good researcher in the industry environment.
Right.
So I did all I can. Lucy had to make her own decision.
Yeah. I always feel like it's like, okay, industry or academia. But is there kind of like other options for people? Like, I always feel like it's just binary, but have you seen?
No, not really. You have industry that you really work on a product, basically, design things for product. There are companies, doing research on more fundamental, more long-term project. But eventually, you have to justify to your company that you can make more product, better product.
Right.
Academic has more exploratory nature. You propose something to do that might become a product 20, 30 years from now, 20, 30 years from now. So other than academic and industry, which are just two sides, you have a lot of in between. Industry Research Institute, right? So you used to be a biolab, right?
Yeah.
It's not a real industry research lab, but it's from the industry side. Yeah. You have national labs, right? You have the DOE national lab. You go there to different from academic, more towards the application, but it's a national, it's not industry.
It's kind of like Sandia, Oak Ridge.
Sandia, Oak Ridge, and really, really good environment, and people are doing an important project there, in this national labs. So it's not only industry-related academia, there are things in between.
Right.
Yeah.
And also I saw that some of your collaborators are not even in America. So how does that kind of back and forth go? And does it kind of like, does the international lines affect any politics involved with the research?
It's important to pay attention to the politics. I mean, for example, the collaboration with China, it has up and downs. We used to be encouraged to collaborate with China years ago. Then suddenly we are not encouraged to do that anymore. And people got in trouble for collaboration with China. An example of my supervisor at Harvard. But for this project, my collaborators are from Spain.
Spain, yeah.
And also I have collaborator in the Army Army lab.
Okay.
So we did not collaborate with. We don't have any problem.
Right.
At that time and even now, I think this the big environment mostly I would say relate to U.S.-China relationship. Large environment really affect how people approach collaboration.
Right. So have to be more cautious.
We have to be cautious. We have to be cautious. I mean, I think that's what the U.S. government want, right? Yeah. We used to think that anything academic is not we don't have to worry about it at all. But even now, like the academic research, we have to be cautious and aware of what could be a problem.
Okay.
Yeah. So there are certain areas, for example, climate change.
Right.
You know, it's not a U.S. problem. It's not a U.S. only problem. It's a global problem. We have to collaborate.
Right.
Otherwise, we save half of the Earth, the other half is not saved. It's not working.
Hence, your green energy direction.
Yeah. So. Yeah. I think that's something that the whole world need to work together on.
Right. And then there's definitely other places and environments who are more invested in green energy than other places. So
right.
So you would ideally want to go with the people who want to invest a lot of money in it, but right? Or politics.
We want to solve problem. All right. We want to come up with a solution for the human society to sustain their lifestyle without creating more climate problem.
Right.
So that's why I'm working on this green fuel, green energy area, because we need to find a alternative path for us to for humankind without just in some way climate is not a Earth problem. It's a human problem because Earth is going to exist. Doesn't matter what temperature, right? Yeah. It can be a fireball, but it's still Earth.
Yeah.
But human would disappear if the temperature is not within the range that we can stand.
Right.
So we are helping Earth to solve the climate problem with a selfish reason because we want humankind to continue live on Earth.
Yeah. So I think that's with the politics. You think it's how do I say this? Is it so when we research, right? We're trying to generally push humanity forward, solve one of humanity's problems, and you could argue that it's for the sake of altruism, right? For the sake of altruism. But I guess sometimes do the kind of like politics and just, again, referring back to your student who I'm pretty sure the politics of academia kind of like deterred her a little bit. In addition, so it's like you said she saw her father was like kind of like a researcher, right?
Yeah.
So it seemed like that sounds to me it was about the money.
Not about money, about happiness.
Happiness, okay. Yeah. Just so not just about the money, but also there's a lot of politics in academia, right? So she just kind of wanted to avoid it. So what I'm saying is, based on kind of like the political climate of academia, do you think that it might, I guess, sunder or like impede academic integrity and academic altruism and kind of like all that? It's a very loaded question, but it seems like there's a lot of it seemed like you alluded to a time where like you could just research, right? Maybe you could just research, but now there's a lot more hoops you have to jump through in order to kind of do the research that you really want.
I think you're right. I think I'm more optimistic than you. I think politics is always there.
Yeah.
right? And if you think about period during the Second World War, like there's also politics related to research.
Yeah.
And for example, we have machine gun bullet holes on the roof of the old chemistry building at Duke because people were working on gunpowders around that time. That's to help the war. That's politics. But politics always affect what kind of research you do through funding and through other manners. So we were never really immune from politics.
Yeah.
It's becoming more a problem in recent years because the kind of the overall relation between U.S. and China kind of changing from really friendly, helping each other to somebody like competitor.
Yeah.
Maybe it will change again. We don't know.
Yeah.
It's really we cannot control the overall environment because that's beyond our capability to control that. But we can work under the big environment to still do curiosity-driven research in academic environment. So all we need to do is to build new understanding on things we don't know. Anything we publish, anything we discover that we don't know before will be treasure for our society. Yeah. It's like understand, for example, understanding the existence of non-thermal effect. It's new. That's good.
Yeah.
People know now. Being able to make certain type of carbon nanotubes, we were not able to do that before. Now we can do it. So those all become a treasure for our society. So I think we still have a lot of freedom to do whatever we want, but always under some restriction. It's always there.
Right.
It's like even if you live in the 1930s, 1940s, that's always political.
So
you know the movie about Oppenheimer. If you watch that, that's politics.
Yeah.
Right.
Right. Yeah.
It's not just for this generation; it's for every single generation.
Right. So I mean, so you can't escape it, but you have to adapt to what the kind of time's like. So
right. But there's just a lot unknown. There's a lot of things that we still don't know.
Yeah.
That's always a job for scientists to do research on.
It's just, I guess it might be a kind of nuisance that. But you guys, scientists are smart, so they'll find a way to do what they need to do within the context of times.
Right.
So you went from your master's to a PhD at Harvard.
Yeah.
So we have a lot of international students here.
Yes.
And you found success as an international student in America. So I guess I'd want to ask, what's kind of like the biggest change in not only kind of environment, but also academic culture environment going from your home country to kind of America? The
biggest change for me is to be someone that always listens to somebody, your teacher, your supervisor.
Yeah.
Just do whatever you were told to do.
Right.
To somebody you think independently. I think the best training I had in US is to become an independent thinker.
Right.
To not always believe what you read, not always believe what others told you.
Interesting.
So the biggest difference between China and the US, if I have to say, is that it's like how independent you are, thinking-wise. Yeah. I think US really taught me how to think really independently and challenging the authority.
Right.
and ask Nobel Prize winner, you might be wrong here,
Yeah,
right?
yeah.
Because in China, if it's Nobel Prize winner tell you this is right, you take it seriously. This is right.
Right. So,
Right. In US, I worked with the Nobel Prize winner as a postdoc. I keep arguing with him and saying, why you think this is right?
Right.
It could be something else.
You have to prove
Right.
your claim. You don't
Yeah,
take it.
to be a good scientist, you have to be ready to challenge authority,
Right.
to prove what's used to be known to be right. I mean, a good example is that people always believe in solid 5-fold symmetry never existed. You have mirror plane, you have 3-fold symmetry, 4-fold symmetry, 6-fold symmetry, but you would never have a 5-fold symmetry in crystal. Theoretically, it makes some sense.
Yeah.
But then people who discovered the 5-fold symmetry in solid, called a pseudocrystal, they win a Nobel Prize on that.
Right.
They prove that the common belief is wrong.
Right.
So that's what a good scientist should do. To keep challenging what's considered to be right, and see whether you can prove it or wrong.
Right. And it kind of reflects in your research.
Yeah.
Taking the road less traveled.
Right.
But awesome. So I think here's a really good stopping point. But something that we do on Navigating Nano is the previous presenter or guest ask a question for the next guest. So the previous person asked dogs or cats. So it's just simple questions like that. And then yeah.
For me, neither, because I'm allergic to both of them.
You what?
I'm allergic.
Oh, you're allergic to both of them. I guess
both dogs and cats.
I guess if you were to own an animal, what animal would you own?
I would have a dog.
Dog.
Yeah, if I'm not allergic.
Right. Well, since you're allergic, outside of that, would you have a snake or a gerbil or something like that? Or
No. Dog is. If I'm not allergic, I'd rather like to have a dog.
Okay.
Yeah.
Sounds good. But Dr. Jie Liu, it was a pleasure having you.
Thank you.
This is Navigating Nano.